Hello, welcome back to NET Physics series. Today we'll be doing the past paper questions for chapter number 8 of waves in the NET series. So here we have question number 1, and it reads, if a radar system designed in accordance with the Doppler's effect, if an airplane is moving away from the radar, the wavelength of the reflected wave from the airplane would be, we have some options. So let's think what is happening. We have a radar, so it's like a satellite, right? And it's attached to the ground. Now we have an airplane. I'll just draw an airplane with this rectangle like thing, and it is moving away from the radar, right? So the airplane is moving away from this radar. This is the radar. Now, the wavelength of the reflected wave from the airplane would be, so we are asked about the wavelength of the wave that would be reflected back from the airplane. So in this case, the airplane is really the source of any sound or any electromagnetic wave, right? It's the source which is giving off the wave. Now the source, if we have this case where the radar, which is gonna observe this wave from the source, is stationary, and the source is moving, but it's moving away from the radar. So we can say that the source is moving away from the observer, and so the apparent frequency would decrease. So the apparent frequency would be less than the frequency of the wave itself, and if the frequency is less, then the wavelength would be higher, right? So the wavelength would be higher. So we can say that the wavelength lambda increases. That's the conclusion that we can make from this system about the wavelength of the reflected wave. So here we have some options. We have smaller than the transmitting wave. That's not true because we have concluded that it's going to increase. Larger than the transmitting wave, same as that of the transmitting wave. This is not true as well. Either smaller or larger than the transmitting wave. Well, clearly it has to be larger because it's moving away, and so this is not true, and hence we choose this option which says that is larger than the transmitting wave, which is option B. Moving on to question number 2, it says that the transverse waves can propagate both in gas and in a metal, not in a gas but in a metal, in a gas but not in a metal, neither in a gas nor in a metal. Now remember, what were transverse waves? Transverse waves are those type of waves where the displacement of the medium, I can write it as displacement of the medium, is perpendicular to the direction of propagation. So we can say it is perpendicular to the velocity. So you can say that if I have this axis and this is a transverse wave, because now we can say that if this wave is moving in this direction, the displacement is really parallel to I mean perpendicular, right? It's perpendicular to the velocity vector. So these are transverse waves. Now these waves cannot travel in a fluid, in any type of fluid. So and the reason for that is because in fluids there is no mechanism to basically drive this motion perpendicular to the propagation of the wave. So there is no way that I can keep the displacement perpendicular to the propagation speed of the wave, that direction, right? So hence in any fluids, transverse waves will not propagate. So we have that transverse waves can propagate. Now they're asking you that they can propagate. So they can propagate only in a metal. So we'll choose not in a gas but in a metal. So that's true, because remember, fluids mean any gas or any liquid is referred to a fluid. So moving on, we have question number 3, and it reads, the speed of sound waves having a frequency of 256 Hz compared with the speed of sound waves having frequency of 512 Hz. Now, we are asked to compare these speeds. So we can clearly see that 256 is really half of 512. So if I divide this by 2, I get 256. So we are asked the speed of sound waves having this frequency compared with the sound waves having this frequency is half as great, twice as great, 4 times as great, same. Remember, the velocity or the speed of sound waves is given as lambda times frequency, because lambda has the units of meters, right? And frequency has it is something like 1 over t, so it has the units of 1 over seconds. So this makes the units of meters per seconds, right? So if the frequency is high, then the speed will be high. Now in this case, 256 is 2 times as high as 512 is 2 times as high as 256. So the speed of sound waves having a frequency of 256 Hz compared with the sound waves having a frequency of 512 Hz. So we are comparing this one, 256 Hz, with this. So at this point, you might be thinking that if the frequency is increasing, then the velocity should also be increasing, right? But that's not the case, because the speed is going to remain constant. This thing is a constant. And what really happens is, by changing frequency, the wavelength is affected, and that's why the speed remains constant. So it's something like frequency is increasing. This implies that the wavelength really decreases. Speed will not be affected, and hence the correct answer is same. So the speed would remain same. So let's move on to next question. We have question number 4, and it reads, when source is moving towards observer with velocity us, so this is the velocity of the source, and it's moving towards the observer, then the modified frequency would be, so remember, we learned in theory that the frequency, new frequency, if the source is moving towards the observer and the velocity is given for the source, so the observer really is stationary, right? So the observer is standing still. So we saw that the frequency was given as f prime equals v, which is the speed of sound, divided by v minus us times the frequency of the wave originally. So this means that the correct option is this one, right? Option B, because we have v over v minus us times f, which is exactly like this. So with that, let's move on to the next question, question number 5, which reads that the frequency of the first harmonic of a string stretched between 2 points. So a string is stretched between these 2 points, and we're given the first harmonic as 100 hertz. So that's the first harmonic. Now, first harmonic is F1, which is given as 100 hertz. They're asking you the frequency of the third overtone. Now, third overtone really means fourth harmonic, right? So whatever overtone do I have, I'll just add one to that, and that's the harmonic that you will be dealing with. Now we are asked the frequency of really the fourth harmonic. So we know that the expression is Fn equals n times F1, right? So n is the number of harmonics, so we are having 4, so fourth harmonic. This implies that F4 is 4 times F1, which is 100 hertz. So this makes it 400 hertz, and hence the correct option is option C. Now let's move on to question number 6. The fundamental frequency of a closed organ pipe is 50 hertz. So this is the fundamental frequency of a closed organ pipe. So these two are the important points in this question at this point. The frequency of the second overtone is what? So second overtone for a closed pipe, second overtone implies fifth harmonic. Second overtone implies fifth harmonic. So the fundamental is given as 50 hertz, right? So the fundamental is given as 50 hertz. We have to find the fifth harmonic, which would be F5, 5 times 50 hertz. And that is simply 250 hertz. So the correct option is option D. Now let's move on to the next question. We have question number 7, and it reads that an organ pipe open at both ends and another organ pipe closed at one end will resonate with each other if their lengths are in the ratio of. So will resonate with each other implies that the frequencies are the same for both of them. So we can just say the frequency for first organ pipe is equal to the frequency of second organ pipe. Now we know that for this pipe, the frequency is given as the pipe that is open at both ends. Remember, it looked something like this, where it's open at both ends, and we can have something like this, or we could have, for the second one, we could have, if it's still open at both ends, we could have the same pattern being repeated 2 times, really. Something like this. And for the pipe that is closed at one end, we have something like this. So it's closed at this end, and for the first one, I'll just have something that looks like this. 1 second. Yes. Something that looks like this, right? And all of this part is filled. Similarly, in this case, these were filled. And for the other harmonic, you could have something that looks like this. right? So this is really touching the point, and it's like this. Now in this case we have lambda, the wavelength, the length is really lambda by 4, while uh, in this case it is really lambda by 2 for this one. So the frequency for the pipe that's opened at both ends is given as V over 2L, and for this one which is closed at one end and open at one end, it is given as V over 4L. So the ratio of these two frequencies would look something like, so if this is 1, so this would be 1 and length 1, 2 and length 2. The speed of sound is a constant, so it's going to remain constant, and the ratio of the lengths can be computed as V over 2L1 is equal to V over 4L2. V goes away, and if I write this as L1 divided by L2, this ratio is equal to 2 ones are 2, 2 twos are 4, so this is 2 over 1, which means it is 2:1, which is option C. Alright, so let's move on to question number 8, and the question reads that the frequency of the nth mode of vibration in a string stretched by some tension T and having a mass m and length is given by what? So we have to find the expression for the frequency for any nth mode of vibration, which is really for a string that is stretched, and the stretching force is this tension T in that string. So we know from the notes that the frequency for any nth mode is given by n over 2L times square root T over m. This is the case for the stretched string. So the expression that looks like this over here is n over 2L square root T over m. So that's C. Moving on to question number 9. The diagram represents a stationary wave on a stretched string. So this is a string that is stretched, and it's really closed, you could say, at both ends. So really what it means is that you have nodes at these two ends. What is represented by point P and the length x? So this is the point P, right? This is the point P. Let's make it clear. And point P is what? We know that when the two waves interfere destructively, they form nodes. So at point P, we have a node. And this is the length x. Now we know one wavelength is one wave that oscillates completely as up and down, right? So that's x represents, this is x, it represents one wavelength. So point P is a node and length x is one wavelength. So node, one wavelength. So the correct option is option C. So moving on to question number 10, we have, if the number of loops of a stationary wave are increasing, then lambda increases, lambda decreases, remains the same, or may increase or decrease. Number of loops is, by number of loops they're just referring to the value of n in the expression. So we know that they're talking in terms of lambdas, right? So we know that lambda for any mode or loop n is given as 2L by n for a stationary wave, which just means that lambda n is inversely proportional to this n. So if n will increase, number of loops will increase, then lambda must decrease. The wavelength will decrease. So that's option B. Moving on to question number 11, we have a sinusoidal wave is traveling towards the right as shown. So this is the wave and it's moving towards right. Which letter correctly labels the amplitude of the wave? Now, first, before coming to this diagram, what is the amplitude of a wave? So if I have a wave that is like this, time is here, we have x position here, and a wave looks like this, then the amplitude of the wave is the maximum distance the wave will travel before changing its direction. So this point is where the amplitude of the wave is. So if I go from here, this point, and read the value of this axis, that's the amplitude of the wave. The same can be said for this thing, which is this point, right? So here it's moving in this direction and then here it moves in that direction. The absolute of this thing, these two values would really be the same if there is no damping really in the system, right? So this would be negative and this would be positive. So the absolute value from here is really the amplitude. So the amplitude is represented by this line, this one, right? Or this line, this one. So in this figure, which line is the amplitude of this wave? Note that this wave is traveling over this line, right? So just one second. So it's traveling over this line really. And so the amplitude should be something that is from here to here. So we have some options at our disposal. So from all of this, this is the one that we'll choose, and it's not clear, but it's D, right? And the correct option, which says D, this one is option B. So that's what you'll choose. This is the amplitude of the wave. Moving on to the final question, question number 12, we have a string of length 2 meters fixed between two supports vibrates in two loops. The distance between node and antinode is what? So we have a string and the length of the string is 2 meters, but they're saying that it's vibrates in two loops. So it will vibrate something like this is one. Let me just try and draw it more neatly. This is one, and then we have two. So, well, this is a very rough sketch, but you get the point, and it's fixed at these two ends. And so that we have well, actually my mistake, I should not really draw it like this. By two loops, what it really means is, let's try to be more accurate. Let's draw these axes. So one loop will look something like this. That's one loop. Now the other loop, so the other loop is something like this. So this makes two loops because this is one loop and this is the other loop. So that's two loops. Now the string is 2 meters, so the loops are divided into equal 1 meter and 1 meter. So this means that the wavelength, if you look at the wavelength, it is from this point to this point. That's that's 2 meters, right? So I can say that lambda by 2 is equal to 1 really. Now, the distance between the nearest node and antinode, so this is where we have antinode, and here we have node. So this is node, this is antinode, this is node, this is antinode, and this is a node again. So that the distance, if you look at this diagram, it's clearly lambda by 4. And if I put the value of lambda, which is 2 meters, we have 2 by 4, which is 1 by 2, which means that the distance is 0.5 meters, or in centimeters, that's just 50 centimeters. So the correct option should be option A.